is Camila, and my partner Gabriel and I will be talking about a replication control protocol called Gossip, also known as Epidemic. This protocol is widely used by distributed systems today to make sure that data is getting disseminated to all nodes on a network. But before talking about the Gossip protocol, I wanted to do a review on available copy protocols. As you may recall from last lecture, Gossip architecture, Gossip protocols are part of available copy protocols. These protocols provide the highest data availability and data reliability of all replication protocols that do not regenerate failed replicas. However, they do make a big assumption that network partitions are either very unlikely to happen or unlikely to cause conflicting updates. This, as we saw last week, can cause network partition problems. A common feature of all replication control protocols is the use of metadata to record the states of the replicas. And the way they do this is that they keep a version number that is an integer that gets incremented every time the replicated data gets modified. Okay, so what is a Gossip protocol? The Gossip protocol is a type of available copy protocols that supports file transfers between hosts on a network. And what's key in this is that it does it over decentralized networks. This protocol is based on the way viruses or rumors are spread. As you know, rumors in societies can travel very quickly and reach almost every single member of the community. And most importantly, they don't need a central coordinator. And this is what makes Gossip protocols scalable and fault tolerant. Similarly, according to epidemic theory, starting with a single infected individual, the time to infect the entire population is proportional to the log of the population size. And one clear example is the coronavirus, and I've included a time lapse of how quickly it spreads throughout the entire world. So what is Gossip trying to solve? In distributed systems, you need to know sometimes when other nodes are dead, you need to know when nodes are becoming alive, you need to get information about other nodes so you can make local decisions like knowing which node should handle a request. You need to learn about new configuration data and agree on data values and so on. So this is what Gossip is trying to solve. It's trying to solve the multicast problem, which is how do we get information from one single node to the rest of the network. And although you can use a common centralized approach, which is this one, which is to have a centralized server like a database and all of your other nodes query it for information. However, this actually introduced a lot of availability and performance issues for large distributed systems. And so instead, a Gossip protocol is simple in concept. Each node sends out some data to a set of other nodes. This data propagates through the system node by node, kind of like a virus, and eventually data propagates to every single node in the system. And this is what we call convergence. And to explain this, I am going to show you a simulation. So let's assume that we start off with 40 nodes in our network and we set fan out to 4. Fan out just is how many nodes an infected node will send its message to in every single cycle. So in the very first cycle, we expect that this node can infect 4 other nodes. Great, that is what we see. We see 1, 2, 3, 4 nodes getting infected after the first cycle. And if we fast forward, we notice that this keeps on repeating until all of the nodes in the network become infected, or in this case, red. And as we can see here from this simulation, the nodes in the network were able to reach convergence after 3 cycles, which is very close to the theoretical number of cycles. Now let's say that instead of 40 available nodes, we actually have 120 nodes in our network. We'll keep fan out to be 4. And what I want to demonstrate, what I guess I want to see, is how many cycles it takes when we increase the number of nodes by 3. So I'm going to hit play and let the simulation do its work. And as we can see, the number of nodes infected increases exponentially after every single cycle. And there we go. As you can see, the number of cycles that it took for all of the nodes to become infected when we have 120 nodes was only 5 cycles. This kind of proves the point that gossip protocols are scalable. In general, or hypothetically, it takes O log n rounds in order to reach all of the nodes. And if we keep on increasing the number of nodes, we won't see that big of a difference between. As we saw in the simulation, in each round, every node contacts another node at random, and it either receives or it can transmit a piece of information, or it can do both. So these are the 3 basic messaging strategies: push, pull, and push and pull. In the push algorithm, each informed node randomly picks another node and sends its message or update, whereas in the pull algorithm, each uninformed or uninfected node randomly picks another node, and if the selected node has information or is infected, it receives its message. And lastly, the push and pull is a hybrid. So in push and pull algorithms, all the node pick another node at random and exchange their message if either node is informed. We noticed that a lot of the papers preferred using push and pull algorithm, and the reason behind it was highlighted by the Karp et al. Paper, which showed that the number of transmissions or the number of cycles can actually be reduced significantly when the rumor is sent in both directions. That is, when using both push and pull rather than only push operations. Gossip algorithms have been proposed and are used nowadays for many distributed applications. In general, they're used in applications where consistency can be lazy, meaning that it's not crucial that all nodes see the same data at the same time. However, what they can count on is high partition tolerance and high availability when they use gossip protocols. Some of the applications that Gabe and I found online of the gossip protocol is database replication, and we see Cassandra being one example of using gossip protocols to do that. Gabe will be talking a little bit more about this. Another practical use is information dissemination. So how do we get one node to communicate to the rest? Cluster membership, and also failure detectors. And another company that uses gossip algorithms is Amazon S3. Some advantages of gossips are they're highly scalable. In general, it takes O log n rounds for a message to reach all the nodes in the system. They're also highly fault tolerant, as we were discussed earlier. They're robust, meaning there is no node that plays a specific role in the system. Therefore, if a node fails, it will not prevent other nodes from continuing to send information to the system. So this implies that a node can just join and it can leave whenever they please without disrupting the quality of the service. They can also offer convergent consistency, and as we saw in the simulation, the information is spread exponentially. And it's also a very extremely decentralized form of information discovery. And lastly, they actually are very simple algorithms and they require very little code compared to other algorithms. Some of the weaknesses of gossip are they're not very efficient. Messages can arrive several times to a node, and this redundancy consumes most of the bandwidth. And we kind of saw this in the simulation where our actual number of cycles was a little bit higher than the theoretical number of cycles. Gossip protocols are also slow compared to multicast. The average rate to send a message is 1 over log of n. We also have latency problems. Because this algorithm is periodic, if a message has a new message, it won't be able to send it until the next cycle. And that adds to normal latencies like network latency. It's also very hard to reproduce and debug given the randomness nature inherited with these algorithms, so you can expect a lot of problems that arise during runtime. And finally, most of them rely on non-scalable membership protocol. And now Gabe will be explaining a little bit more about the gossip architecture.